provide a brief introduction to the project and where today's topic fits in more broadly, and then Ted will introduce Taehyung more specifically for the lecture today. Okay. So first I have to mention that this lecture is part of the Paige Barber lecture series. The transduction lecture series is part of the Paige Barber program. And this is a lecture series founded in 1907 by Mrs. Thomas Nelson Page to be in any field of the arts and sciences that presents some fresh aspect or aspects of the Department of Thought. And traditionally, the Paige Barber lectures have been delivered by one person who gives maybe 3 lectures, and those would be published. And but in recent years, thanks to Meredith Wu, Dean of Arts and Sciences, and her team, they expanded the program to support interdisciplinary projects like transduction. So I apologize to the students in transduction who've heard this many, many times, but for those of you who are new, we have Dean Wu to thank for this opportunity. But today I have a great opportunity to also thank Ted in the music department. It turns out that without Ted and without the music department, we never would have had this project at all. Because it turns out you need 2 departments to submit a Paige Barber proposal. And the problem that we had with the transduction project is that we had about maybe 20 or more departments in many, many schools. But it wasn't obvious what that one other department should be. And it was Ted who stepped up in the music department. Richard Will, who stepped up and supported this project in its entirety and submitted a letter of support when it was very much needed. So thanks, Ted, and not only for the project, but also for suggesting Taehyung deserve a set of fit for the project. So I just want to speak very briefly to where today's topic and event fits into the transduction project more broadly. And in fact, this is one of maybe 2 or 3 other fields we've studied this semester, looked at this semester, that where you don't really even have to explain what the word transduction means. It's so much a part of the field of computer music. And the same might be true for cell biology, where people know straight off what cell signal transduction means. Okay, it's a conversion of one kind of signal to another through some kind of interactive medium. Okay, and again, in computer music, it's all about converting signals and energies from one to the other through interactive digital or analog media of various sorts. And likewise, in computer music, human interfaces play a very important role, whether we're talking about the musician, the composer, the computer user, encoder, the archivist, as we learned about today, the listener, and more. And in the discussion earlier today with Taehyung, you mentioned that the most difficult part of the work is in fact it happens here. Okay, it happens in your head because you have to make choices about what to do with so much data and with such an abundance of different kinds of technologies. So in computer music, what happens in your head is a very important human interface as well. Choices that you make. Today's session links to some of the previous sessions in ways that are both obvious and not so obvious, perhaps. The most obvious link is that earlier this semester we heard Doug DeSimone from cell biology talk about transduction and how actually the process of hearing at the cellular organ and organismal levels. So that's an obvious link to session on computer music today. And last week, like Jason Kelly Johnson's presentation about future cities labs and maker spaces, Taehyung's work is also very much a combination of sort of the creative and artistic with the involving design or composing and aesthetics, but it's also highly technological and very much about engineering. So those are some themes that are carrying over from last week as well. And also, last week we, in Jason's session and today's session, I think we'll see they're very much focused on sensing and responding to environments in creative and interactive ways, and making even invisible things perceivable in new audible and visual ways. And I guess the last thing I couldn't help but mention after our conversation earlier today is that a less obvious link between the Transduction project and the Citygram project that we'll hear about today is that they share some similar motivations. So it turns out that environmental health, very broadly defined, motivates and pervades the Transduction project, both in its very conception as well as in particular sessions, like Loma's Gubra's session on environmental health. We have an upcoming session on community discussion on the effects of devices on thinking, learning, and community. That'll happen at the Bridge on Tuesday, April 8th. And then we've rescheduled Natalie Jeremijanko's visit, and her visit is all about a very unusual conception of an environmental health clinic at NYU. So hopefully you'll have a chance to meet her and perhaps collaborate with her one day. But we learned in the discussion earlier that Taeyong's Citygram project is also motivated by environmental health concerns and well-being. So I can't wait to hear more about that and other aspects of your work. And once again, thank you for coming.
It's an honor and a pleasure to be involved with Cassandra Fraser's Transduction project for the Department of Music and for myself, and for the Paige Barber lectures more broadly. And it's also an honor and pleasure to introduce Taehong Park, who is a friend and someone I've known for 15 years and known of for a little longer. It's true. And I'll just say that, let's see, what should I say about Taehong? So Taehong grew up in Germany, in the Congo, and Korea, and was educated as an undergrad in Korea in electrical engineering and computer science, and was also a pop star in Korea, playing the bass and I'm sure singing, and crooning. And he worked for LG, which at the time was called Gold Star. At LG, I have an LG television I was telling Taehong, which I bought with confidence, knowing Taehong. I'm sure that kind of attention to detail that Taehong brings to all his projects is still, part of the soul of the company.
This is still working.
Yeah, it's still working. In this town, that's with our electricity situation, that's actually kind of impressive. And then came eventually to Dartmouth College, where there's a master's program in electroacoustic music, where I had been as an undergrad, and then went to Princeton University to get his PhD, where we overlapped for a while. And we overlapped in the following way. I was there, and then Taehong came, and then Taehong got his PhD, and I was still there. Taehong got a job. And Taehong got a job at Tulane, and he started a really excellent music technology program there, a very rigorous and effective music technology and composition program there. Hosted ICMC, which is the International Conference of Computer Music, and did an incredible job. Actually, it was a joint American and international conference, the first time that had ever been done. And eventually, after a few years, made his way to NYU, where he's now professor in the music technology and is the director of composition. And so this project is a fascinating project. I learned about it, before I learned about it from Taehong, as I should have. I learned about it through another co-collaborator at NYU, whose work some of you may have encountered, Luc Dubois, who's a composer and programmer and multi-and artist, multimedia artist. And it was just an incredibly exciting project. And so I later spoke about it with Taehong, and I realized it would be a great contribution or addition to this series. And so it's a great pleasure. Please help me welcome Taehong Park.
Thank you so much. First of all, thank you, Professor Cassandra Fraser and Professor Ted Coffey for inviting me to this wonderful gathering, and we should do this every week. And thank you to UVA and Paige Barber from New Orleans, Bourbon Street syndrome. And if you have any questions, please feel free to ask at any time. I won't respond, but still, you can still ask. And so yeah, today I'll talk about a project called Citygram, and the subtitle is Mapping, Sonifying, Visualizing Dynamic, Visual Urban Environmental Energies. That's a mouthful. So what does all this mean? We'll soon find out. And if you need to reach me by email, I'm THP, Taehyung Park 1. It's kind of amazing because I ended up at NYU like a year and a half ago, and I'm the first THP. So, as Ted sometimes calls me. So here we go. And I'll talk about four main modules in the Citygram project. And one very sort of important concept is the notion of non-ocular invisible energies, dynamicism, things that are always in flux, sensor network, big data, science, and sonification. So those four big sort of blocks kind of define the Citygram overall space. So Citygram actually started around 2011 in the fall, and usually you have these one-phrase descriptions, which are very long, and this one is actually not so long. So the one-phrase description is something like this: mapping and investigation of non-ocular spatio-temporal energies. So what does that mean? We'll soon find out. So the motivation and origin of Citygram came from observing current mapping systems, right? Even like, let's say, 10 years ago, we didn't really use these guys to navigate, right? Back in the day, especially when I was a little boy, I definitely remember my parents always whipping out that big map and then trying to figure out where destination B is, and going through the thing and finding out that that road no longer exists, and so on and so forth. Nowadays, either we have a GPS, I don't have a GPS, but I use my phone with GPS, and that allows us to, actually that's what I used to come to this wonderful campus. But at the same time, the observation was that all of these maps, whether they are modern or not, really represent visible things like parks, streets, rivers, mountains, all those things that we can see. And those visible objects are usually very static, and they don't change much over time. For example, Google Maps takes snapshots every 1 to 3 years for their mapping systems. And that makes sense because buildings don't disappear every 5 minutes. Depends where you are, but they don't change in form or shape every 5 minutes. And that sort of sampling rate does not need to be at the millisecond range, nor at the second range. It can be actually very large. But what about non-ocularity in maps? Meaning those things that we cannot see and do not see. What about those things that occupy the environment, our surroundings, and us every day, every minute, every second, every millisecond, microsecond? What about those things? So that's how the idea came about, trying to think, that would be a cool project to do because those things don't exist. And those things are very important in our daily lives and in our well-being. So for urban environments, the urban spatial acoustics are basically underrepresented, or they don't actually exist. And I'll try to explain what that entails later on. And one of the reasons it's very difficult to create these so-called sound maps is that the dynamic problem has not been solved. Meaning, if I do this, it happens for like maybe 1.5 seconds or shorter, then it disappears, right? So there is no residual element that you can take the average of in this room and say, this is the dB levels. It just doesn't work that way. Meaning, acoustic energy is always in flux, right? And which is a good thing, because if we had like acoustic energy here in this room at 120 dB all day long, we would all go nuts. So that's a problem, and that has not been addressed because the way we measure noise is you have folks going out with these devices and recording the dB levels and taking the average over a week or over a month, And that actually does not work because just as I said, acoustic energy just disappears immediately, depending on the space. So the dynamic problem and the flux of acoustic energy is a problem, so that has to be solved. And that's how the Citygram name came into existence. If you think of city as a city, gram as something that's in flux, Citygram. So it's not related to Instagram. People ask me about Instagram all the time. I actually didn't even know there was an Instagram, so I don't like to post my pictures on the web. Call it privacy. And other people do it for me, so I can't control that. But it's kind of interesting because I'm trying to map sound, so it's kind of weird. But that's where the name comes from, city, and sort of trying to capture the dynamicness of urban environments. So currently we're in iteration 1, and iteration 1 basically comes down to mapping sound in real time and visualizing it and analyzing it in real time. So how does that all, how is that created? This system overall is what people often refer to as a cyber physical system. So you have the cyber, the virtual side, or the software side, and you have the physical side. And combining those two, you create this, basically this software plus hardware sensor network. And what happens is we deploy remote sensing devices, I call them RSDs for short, and you have a server. So in this picture here, you can see all the sensors deployed in urban areas or whatever geographic area. You have a server that takes in, that receives streams of data, feature vectors, as they're called, and I'll explain those shortly. And then you can do things with those feature vectors. So what these RSDs, these remote sensing devices do is that they dynamically capture the sound. The server, actually the RSDs also do distributed computing. So basically I'm using these Android-based devices, and these are very powerful machines, and they do distributed computing, meaning they're kind of like ants. When one ant works, there isn't that much work that one ant can do, but when all the ants join forces, there's a lot of work that can be done. So that's the sort of distributed computing paradigm that we're using. Then we can visualize all these feature vectors, energies, and whatnot. And currently, we're focusing on noise pollution and soundscape. One of the reasons noise pollution is a very important topic in well-being and urban environmental health-related issues is that more and more people gather in cities and want to live in urban areas. These are called megacities, and it is expected that 80% of the population will live in megacities the next 50 years or so. That's a projection, so you'll have an explosion of city dwellers that will introduce unimaginably big problems, including noise pollution and other forms of pollution. And this is a good time to try to figure out how to best address these issues through measurement, analysis, and perhaps even contribute to policy making of urban development. So that's kind of the explanation of cyber physical systems. So what we're doing is developing server client computing technologies, and I'll explain those very shortly. Does this all make sense? It's actually really straightforward stuff. I'm sure you've heard of these things at some point somewhere. So one of the very important things that we need to deal with is the RST development, so the sensor development. I think there are basically two approaches when researchers and engineers think about remote sensing devices. There's one side of the spectrum that thinks that spending $10,000 on an instrument is the way to do it because you can get the best quality sound or the best quality measurements and have us provide the funding for that. Then there's the other side of the spectrum, which is the one that I'm pursuing, and that's using technologies that exist that are very cheap and that can encourage community engagement and citizen scientists to get involved, and that's how our system is built. So in the beginning, I kind of started in the middle. We had bought these mini computers, Alex mini computers, basic Linux system, has all types of I/Os, and it's like this large, and that cost maybe altogether maybe $700, $800, and it's waterproof and it's great. It's got Wi-Fi, Ethernet connections, all kinds of I/O, including audio, and you can attach a lot of sensors. To me, that it seemed promising and it would do the job, but I thought that this was way too bulky, looks kind of scary, and was rather expensive. So we went to the sort of area that we're kind of comfortable. That's my controller and basic stamps and Arduinos, and then like 3 years ago, I think, was the Raspberry Pi sort of dropped from the heavens and out in labs, and we're like, oh, this is awesome. And we tested the Raspberry Pi. It was this really small Linux-based computer, basically, and with lots of I/Os and whatnot. But at the end of the day, the Raspberry Pi is actually not as powerful as it can be, and it's also pretty fragile because you've got to like plug in things, and it's not very robust. And although it's very cool, and we all like cool things, but you also have to be practical about things. So the Raspberry Pi was abandoned. So we were kind of scratching our heads and trying to figure out what the best way to would be to address the RSD issue. And then it basically dawned on me and some others that actually one of my friends was doing some research as a computer scientist, and he's doing research in volcano activities, and he said, I'm using LG phones that cost like $30 a pop, and he's got like 10,000 of them stuck into a volcano, and they all send signals back to the home base, and he's getting real-time sensors through accelerometers, readings of the volcano. And like, dude, that's what I need to do. And he showed me the thing, and it worked really straightforwardly. And I'm like, this is where the answer lies. Because these are very powerful computers, and this guy has like, I think like 6 or 7 sensors built in already. So I'm like, this is look no further. And that's how I began to think about the RST space, the remote sensing device space. And I'm like, okay, these things are still very expensive. Although in like 5 years' time, these will cost like, what, $10 or something? Or like 10 years' time, maybe $10. And in 10 years' time, no one will use these guys. So it's a good way to recycle them, actually. But even before that, like immediately how to make these things cheaper. And I thought, yeah, wouldn't it be great if we didn't have the screen, because we don't need that? And that's what this guy is. These are called actual mini computers, and they're like maybe this big. I didn't bring one today. And they basically don't have a screen, and they're exactly like an Android device. It runs the Android OS, and doesn't have a LCD screen or touch screen, and the price drops down to like $40, $50, and boom, you're done. And these guys that we're using right now have a quad-core processor, so you can do all kinds of DSP, and they have I/O built in, USB I/Os, audio I/Os. You can stick in a recorder, basically, an ADC, and you can then record audio. You can add other sensors to it because they have Bluetooth, and have like a sub-module that can, if you use an accelerometer, you can measure vibration, or you can measure smell, and all those things. For first things first, we're like, okay, this is the best solution. And then we came up with the technology to make it actually work, and that's where we are right now. So an Android mini PC, you can buy these off the internet really cheaply. I'll just show you how easy it is. If the internet works. I think things because I'm running this guy. You can search it later. Just do MiniPC Android, and you'll see lots of these very cheap products. These are actually used for building television remotes and things like that. So for something totally different, but it certainly works for this application. So the Android hardware has sensors attached to it already, flexible development kit, and compact and ready to go. And these are very efficient, which means that battery life is actually pretty cool. We bought a battery pack with these guys that it goes for 23 hours without recharging, which is perfect. Because actually we just, well, I'll talk about that actually as well. So the RSD, the remote sensing technology basically has been solved. So you had the option of going the $10,000 route, now you have the option of going the $50 route. Which one would you take? This guy, because it's actually as good as the other guy, probably better in many ways, because there's a lot of fat that's just taken out of the equation, and there's no middle person trying to make things more expensive, and anyone can actually get involved with this. So there are two strategies. So the next problem actually is how to deploy these RSTs into spaces, right? So that's a big problem. And we came up with two types of strategies. One is permanent, and the other one is impermanent, or fixed and mobile. So when we have these type of RSTs, these can be just a fix. I call it the Velcro and stick technique. It's a new sort of catchphrase that you'll probably hear, and just Velcro stick and you're done. Because they have Wi-Fi, they have, all you gotta give them is a little bit of power, and they should just run automatically. So these are the permanently fixed ones. For example, in New York City, we have 11,412 payphones in the city. And how many of you have used payphones in the past 2 minutes? Yeah, I thought so. No one. See? No one's used payphones in the past, like, I don't know, 5 years or 1 year. 2 people. Yeah, that's basically 3 people. But that's basically the state of our payphone system. We don't use it, and I got my cell phone in 2005, and the reason I got my cell phone for the first time then is we went through Hurricane Katrina, so I do want to apologize for the weather. I think I have a problem of attracting bad weather. Like in New York City, I brought, I think, Sandy with me, so it's all, you can blame me for that. But yeah, payphones in large cities are becoming obsolete. But payphones in large cities need to exist for a number of reasons, especially for emergency type situations. You need the landlines, you need those in place. During Hurricane Sandy, for example, they were really important. And also during Hurricane Katrina in New Orleans, they were very important. And also, apparently they bring in about $14 million a year in terms of revenue, not through phone calls, but through advertising. So the city wants to keep it, and they probably spend a lot of money putting in the infrastructure. So that's a perfect way to deploy our fixed RSTs. So immediately, if New York City, for example, embraces this notion of having sensor networks, then we'll have 11,412 sensors up there pretty quickly. And New York City is also trying to, they have some pilot programs where these payphones are just Wi-Fi hotspots. And I think we have like 120 of those in the city. So that's actually a really nice mechanism because they have electricity, they have power, and they have communication. So the actual notion of Velcro and stick does stick in this case. Lampposts, traffic lights, parking meters, and so forth. These are the sort of permanent fixed deployment strategies that we're looking into, and we're currently working with New York City Mayor's office to try to make this happen. Also, a good friend of ours, that probably knows Ajay Kapoor. He's a professor over at Cal Arts, so we're trying to use the Cal Arts campus to have some of these sensors to look at noise pollution and how that affects learning and so on and so forth. So these permanent systems, permanently fixed RSTs, this is sort of the solution we're looking at. Then you have the mobile and crowdsourced mechanisms, and mobile apps like mobile applications such as Android OS or Apple iOS. Basically, our phones and tablets and whatnot, we can opt to download our software, and we can enable them or close them anytime we want, and we can become what we call streamers. It's like the title of a movie, actually. And you can sort of engage and help in providing sensing your environment and visualizing that on maps. So what happens when we use these streaming features is that we use feature vectors, and that's not the audio signal itself, it's characteristics of the audio signal. For example, is it loud? So like one-dimensional scale, loud, soft, right? Or is it bright? This is called the spectral centroid, bright or less bright, and things like that. So these are sent to the server, and the nice thing about feature vectors is that they cannot be inverted to get the speech back, meaning just with loudness levels, it's impossible to recreate the audio signal. Same thing with respect to brightness. It's kind of like you have that treble knob on your audio hi-fi system. You cannot use that no matter how fast you go back and forth. You can't really recreate the audio signal. So that helps with the privacy issues, and there are many. And I always get questions about that. So if you have any questions and concerns, please let me know, and I'll try to address those as well. So the mobile app environment, desktop, laptop applications. So anyone with a computer and a mic internet connection can become a streamer. So that there are programs like MaximSP, PDC Collider, Chuck, MATLAB processing, and so on and so forth. Anyone with a computer, just register on our website, and your node will pop up on the Google Maps interface, and I'll show you that what that looks like. So streamers basically become citizen scientists. Right? You can engage in the research, you can have access to all the feature vectors of past, present, and perhaps use that to model the future and make sense of what's happening in terms of noise pollution, how that affects different areas of city life and well-being. And I'll talk about that shortly as well. And there are ways to also use this in a musical sense, and sonification and actual performance. I'll address those issues as well. So here's a typical sort of some of the tools that we developed. We're also collaborating with this center called Center for Urban Science and Progress. This started last year in 2013, and they are providing their server to us. So it's a pretty incredible system. They have 2 large memory servers. Each has 1 terabyte of RAM, access to 720 terabytes of persistent storage, 20 distributed computer nodes with a total of 1,280 cores, and 2 terabytes of RAM with storage capacity up to 240 terabytes distributed, and 720 terabytes persistent. So it's a nice server that we can do a lot of processing on and store data, historical data. And this is the typical system. We have these RSTs in urban spaces. All this data, raw data, is sent to the Citygram server. Then you have users over the world being able to access that and visualize it. And here's some examples of the Google Map interface, MaximSP, Android app, and so on and so forth. And I'll show you a quick sort of demo of the current system. It's still in its prototype stage. And basically what's happening here is I'm basically, you can see the time. We are visualizing RMS energy, root mean squared, which is basically the loudness of a space. And these nodes are RSTs, so there's one in Central Park. So it gives you a nice sort of street view. Gives you the RMS data, timestamp. This is actually from the past, so if we also store past data. And this is still in progress, but there's also, if this is live, there's like a play button. You can actually hear the space if you want to. So the way I try to explain the utility of hearing the space is I got twins, they're like 4.5 years old, and I'm thinking to myself, okay, this is Sunday after lunch, 1:30 p.m. Let's see, where's the quietest park I want to take my children to? Like, no way of knowing. So I just look at the Google map, listen to the sound, and like, okay, let's go over there. Very practical sort of situation. So yeah, I mean, you can access the website anytime, and basically, if for example you download our app, register, and enable it, then I guess it's really able. Is this correct? I mean, you'll basically see like a little note appearing, and you'll be able to see the energy in that space. They call it the vibe meter. and you can also hear the space. For example, if I had my ran out of batteries, if this were working, you could actually hear this space. And what I also employ is a voice blurring algorithm, so that when you speak, you can't hear what's being said. It sounds like using grammar synthesis. So you just kind of focus on the voice band, scramble that, so you can hear the space, what it sounds like, but you can't hear what's being said. That's sort of like a feature that we included into the Citygram system, so that you can actually hear the space without compromising, or trying to not compromise privacy in speech and so on and so forth. So imagine we have like thousands of these, and you can zoom out even more, and if you imagine Google Earth, and having Google Earth and all these things kind of drop in real time, you just spin it, you can actually almost be like Superman and fly over Google Earth and hear what's happening in Kinshasa or Kilimanjaro or what have you. It becomes an interesting, very, I think, amazing interface once it gets to if it gets to that stage. Analysis and visualization. So one of the important things we're trying to do is try to analyze and visualize the incoming data streams, because data is not that interesting at all unless you try to figure out what's going on. And one way to try to figure out what's going on is visualizing some of these invisible energies. Right? It's kind of interesting. How does the acoustic signature change over time, like on a daily basis, or throughout the day, morning, afternoon, and evening, or about the entire week? How does that change over the week? What about a month? What about a year? What about 300 years? What about 10,000 years? What about 1 million years? Can you imagine if we had all this data 1 million years ago? All this data with acoustic energy, and how that, how our Earth has changed and is changing. That would be an amazing thing to have, and we can actually do that right now. That's what we're trying to do here. So real-time heat maps, that's a very sort of proof of concept type visualization format. We're investigating different ways to visualize it, and I think artists actually always come up with really interesting ways of visualizing things. I have to show that our collaborators over Colloquium did for us. If I can find it. I hope that's the way. Underprepared. Ted, you had a question?
Oh, yes. Now, you're positive there's no way to reverse engineer the granular synthesis?
No, it's a very, very good question. And there's always ways, I think, to try to get some form of the original signal. And by no means am I saying that it is impossible to do for this system. there are hackers and crackers. Crackers? My English isn't that good. There are people who can infiltrate machines and get what they want. So it's not foolproof. And I think the only real way to combat this type of, in a way, it's a surveillance type system. And the way to address these issues is to be completely transparent. That's the only way. It's not the technology that's going to save the day. As I said, we put in these mechanisms to blur the voice and just do feature extraction and whatnot. But at the end of the day, I think it becomes an issue of transparency. And once this is transparent, completely transparent, and everyone can get involved and you know what's happening, it's going to be totally open source, that's how you address the issue. And it's not a technological problem, I think. There's always a way to figure out something that the technology will not be able to hide from you, or it won't enable an encryption. You can always crack an encryption algorithm or whatever you have. So yeah, I think it's not an issue of technology. It's actually an issue of policy and making everything transparent. And this will, as I say, belong to the people, right? So that's the way to address this. I can't find the file, so it was there.
Within Citygram, in your Citygram folder?
It could be. Very strange. Let me just try one more thing. I can't find it. I think the NSA took it. Okay, so it's basically a visualization done in processing in real time. It shows you, it looks really pretty. It's not that informative, but there's ways to use this in an artistic way. And that's what that example was going to be. So visualization, analysis. So what we're trying to do is analyze the sounds. In one of the things we're trying to do is analyze the sound in terms of identifying what kinds of sounds the sensors are picking up. For example, if there's somebody sort of coughing, then we'll like cough. Or if there's a car passing by, then you can count the number of cars passing by, which informs you on the noise pollution. Or if you have somebody running, then you can hear the running sounds and classify that, automatic classification through machine learning. Or you have a little cockroach running around, you can capture that because they're so important. I'm just kidding. Cockroaches are important, but I don't think we'll be able to capture that. Other things you can capture probably is bird migration and bird ecology and other animal ecology type sounds that are in urban areas, and to follow that and to have to visualize that over a long period of time. Other things we're developing is what we call the SATD. For those who are musicians, you'll love this acronym, but it basically stands for Sound Analysis Toolbox, and it allows you to do all of this stuff on your computer, and it's written in MATLAB with machine learning and visualization, all that stuff. And that will also be totally open source and free for your usage. Another very important research topic is taxonomy, and trying to figure out what the semantic space is for urban acoustic ecology and soundscape. What are the words that occupy a certain space? It's like, okay, we have with the machine-based sounds, we have the sort of natural sounds, we have the animal sounds, we have all kinds of sounds. How do they, how are they organized semantically and physically, and so on and so forth. That's what we're doing. And then the UX development, the user interface development. How are we going to design our user interfaces so that we invite citizens and community members to engage and use this for research or just for fun or in gaming sort of initiatives. you can certainly imagine how gaming could be used in this context as well. I'm not developing at least any gaming type applications, but once the API is available, then you can certainly explore those options as well. So more context, one of the very important goals for us is understanding the environmental urban acoustic ecology. So noise pollution, for example, in New York City, we have a thing called 311 non-emergency call lines, and it's basically people calling about, oh, there's something happening in my neighborhood, and complaining in a non-911 type, for non-911 type situation, and apparently for the majority of the 311 calls, noise pollution is at the top. I think like it's about 80% of the complaints, 311 complaints are noise-based, which is pretty incredible, but it kind of makes sense. It's kind of like, oh, there's a truck that's playing loud music, or there's a party that is just going insane, or there are people shouting on the streets, or we have construction work, or we have too many cars. These types of complaints really are pervasive all over New York City. So that informs us in terms of if we can quantify noise and noise pollution in the city, then we can start to address quality of life, health, and business, education. How does that affect the education of our kids? And you can imagine there's studies which show this elementary school that's near an airport where the students are just not doing well. It's constantly going, it's obvious that it won't have positive impacts on the children's education, but if we go a few steps below that, where the noise pollution is a bit more subtle, how does that affect children's education? There's also evidence of noise pollution, how that affects pregnancies and other diseases that have real dangerous implications for city dwellers. Because just because we don't see it doesn't mean that it's not there. It's actually more dangerous not to be aware of all these dangerous things that are around you. So one of those things is noise pollution. So inform policy making. So you can think about the notion of you can't fix what you can't measure. Right? So that's one thing that we're trying to do. We're trying to at least start to measure some of the noise, and then quantifying it, and you have the data, and you can start to address what is happening in various spaces and whatnot. And then the next step would be connecting all these dots, or all these layers, location-specific spatio-temporal data, such as census data, population features, crime stats, school performance, real estate data, health data, all these things. Now you can correlate and see what's going on. And maybe there are patterns, and it's probably not going to be one dimension affecting the other dimension. It's going to be so entangled in a non-linear way. Probably not a Euclidean distance type thing, but some crazy modulation that happens between the distances, and we're trying to find out how we can inform our living environments by bringing all these different energy types together, and even Twitter feeds and social media. That's very important too, because then we have the semantic space, right? And, during the elections with Romney and Obama, that was this Twitter space was going berserk. Just imagine being able to fold it into the acoustic energy that you were measuring, or whatever you had in that space, and then get a sense of what's going on. Affective computing, it's called, actually. So geotag and timestamp textual data, as I was saying, blogs, social media feeds, news feeds, and so on and so forth. So there's a lot of data out there, and we're trying to collate it and bring it together and see what we can do through machine data, through data analysis. So you need a lot of different experts. The musician is sort of the weird person in the room, but somebody's got to get started. And you need the social scientists, you need the psychologists, you need the doctors who can actually help people with their diseases, and you need policymakers, you need engineers, computer scientists, and so forth. And what we're trying to do is provide a platform where people can come together and use the data to do whatever they want to. One very interesting field for us in this project Citygram is soundification. And soundification actually basically means you have all these different types of signals, and how do you map the signal to sound to make it musical? That's basically soundification. It's actually nothing new. So if you look at a score, right, a musical score, you have ledger lines and staffs, and then you have notes. They actually, these notes are mapped to very specific things, and then these things create music, right? So if you imagine that in a more generalized setting, you have all this data stream coming into a server. Now you can map these data streams into sound and make sense of what's going on. For example, I think we use it daily in our cars. If you have a car and you do like left hand side, yeah, if you go like left, or if you do this, it goes click, 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 click. It gives you that audio feedback, right? If you do this, still that's the same thing, but you get the auditory display type of thing. That's soundification, actually. So giving clues as to what's happening. You can also imagine perhaps the sort of Citygram map being useful for the hearing impaired, actually the visually impaired. Hearing impaired that would actually also help. Yeah, because you can actually see the sound. Right? So for the visually impaired, you can actually have a sound map and hear a sound. What does Zimbabwe sound like? What does North Korea? Now, I don't think they'll deploy our sensors there. What does South Korea sound like? What does Seoul sound like? It's actually possible to do, and we can almost immediately deploy these things because it's totally free and it's totally open source. So as far as soundification and Citygram and performance is concerned, imagine, let's say Ted writes a score and has instructions for me, and I'm in New York, and just he sends it by email and says, okay, be at this location at this time, because we have these sensors installed, and influence the space acoustically, clap, or bring in like a guitar into the things, and then I'll do something over here at UVA, and then you do something over at Beijing, and you have a network performance immediately with minimal cost and with minimal technical complexities. All you need is this. That's it. Nothing else. So you can do that all over the world, right? Because all you need is the internet connection on a computer. So this is called telematic performance. Currently, telematic performance is actually really complicated. They have a lot of equipment that they need to set up. In this sort of paradigm, kind of bypass all that stuff. And there is latency for sure, but it's imperfect. As I said, easy to set up. All you need is a mic, network, speaker, headphones, and perhaps even video camera, which this one has also. And you can have also video. So that's the sort of more artistic, musical side in using Citygram, and you're spatially uninhibited, and quite literally you can have global performance. It's kind of like Skype in a way, right? But this allows you to do everything that goes beyond Skype, because you're actually extracting all these feature vectors and doing more low-level signal processing on the sound and streaming all of that. And so at this point, we're in iteration 1, and iteration 1 is acoustic ecology and noise. So we're looking at noise patterns and basically trying to capture noise. Iteration 2 and subsequent iterations will include other non-ocular energies, such as humidity. Humidity is actually very important, and apparently, I didn't know this, humidity is sort of the #1 enemy for asthma patients. So if you have real-time maps of humidity of any urban space, and just go to Google Maps and send Google Maps because it's quite used, and you can see the humidity levels, then you know where to go, where not to go with your child, for example. Electromagnetic radiation, you can do that as well. Wind speed, temperature, color, brightness, rain acidity, pollution-related energy levels, all with the same technology, just Velcro and stick, and you're basically done. So subsequent iterations will fold in different types of non-ocular energy measurements, and imagine the Google Maps, just like this one, having different layers of energy types that shows you what's going on. The more nodes, RSDs you have, the fuller picture you'll get. So So it's very important that we get the community involved. That's why we're creating all these free tools that you can use. Continually, what we'll be doing is fine-tuning our system, especially the visualization ones, finding context, sort of like voting trends. How does that data, the data we capture, influence voting trends, or is there any correlation with that? Just see what these energy types mean. Jokingly, half-jokingly, I talk about sometimes. It's not in this presentation because oftentimes people laugh. Feng Shui. It's kind of funny, but I believe there is some interesting ways to use those ancient learnings, so to speak, and see how that actually relates to space and well-being and whatnot. Human-animal population climate shifts, as we all know, and that's what we'll continue to do. So the biggest thing that will determine success or even failure of this project is not the technology per se. As I always say, the technology is not that interesting because anyone can really do it, as you've seen here. The real interesting thing is how to deploy these sensors. And I was saying, in New York City, we have 11,412 payphones. So imagine these nodes just becoming those RSD nodes. We'll have like a surface plot of what's going on in the city. And this can obviously be deployed in any city or any place that provides you with electricity and internet connection. So it's amazing, I think, there's amazing potentials in learning more about our environments, especially those things you cannot see. So we have a couple of small-scale, mid-scale sensor network deployment strategies in place. The first one is actually Metro Tech in Brooklyn, New York. It's actually happening on Thursday. So we're deploying about 20 sensors in Metro Tech. And that's what the sky is actually. By default, it goes to Metro Tech. There we go. So this is where the center of urban science and progress is. So you're going to be deploying about 20 sensors here, and also Colloquium campus. Sensors over there, probably like 30 of them. There's also this company called Simply Grid, and they offered us space for our RSDs. Then we're going to go to Union Square, which is also in New York City, and probably like 50 to 100 sensors in the Union Square area where there's a lot of noise. And we're also talking to art galleries in New York City and to make it into a sort of installation art piece for kind of interesting visual stuff that goes on, and the music we can create with it. And the large-scale deployment, I think that'll be the biggest hurdle in convincing the city folks that we can make better use of the payphone systems to improve our lives in the city and inform us in trying to combat different types of problems we have, including noise pollution. So any type of mobile cloud source or any type of computing device will be is actually game like this computer, as I said. So we'll have a sort of a couple of hackathons probably to get the word out. And if anyone is interested in participating or actually being part of this project, just let me know. We're always looking for people to collaborate with. And this is certainly not a project that we can do just by ourselves. It really needs to engage the citizen science portion of your overall gestalt, let's say. So that's it. Any questions? Or did I? Are there any questions?
Yes.
Hi, first of all, I wanted to say thank you for that incredible project that you're working on. It's really, the potential's immense. But I actually wanted to ask you about that. How will you get the lead part of this into, say, the institution near the city? How do you get them to really buy into this and start using the material? Because you could develop this whole thing and sit outside of that very closed network on things and over there. So how do you really make this thing possible?
That's the biggest challenge, I say, the scalability and deployment of on a large scale. How do you convince people this might be good for you? I don't actually know. This may be detrimental because maybe the NSA will just take over the entire thing and slap it in the face. They'll probably do anyway. But as long as you make it more transparent, I think it's harder to do that. But how do you do that? The answer that the solution that we're providing is creating technologies that are easily usable, that runs on any computer device. Like I said, like my laptop, my phone, your tablet, your cell phone, anything that has a mic and a internet connection or cell network, you'll be able to participate. And one way to do that is have interesting events. So what we're trying to do, NYU is interesting in a way because they have a lot of guest artists that are not in the sort of music space, but Ashley Simpson, one of the Simpsons, the husband and wife team, Simpson. Solid, that song. Solid as a rock.
Oh, really?
Yeah. Anyway, like there are these famous artists that come to give talks and have like mini concerts. So what I was saying to the organizer was that we can have this event where we install a number of our RSCs in the space and sort of capture the vibe of the space, and then have that as part of the concert, so that when people visit the webpage, they can feel or see the vibe of the space, not necessarily the concert. So getting the word out that way, into museums or art galleries, getting them involved, making it an art project, that alleviates sort of the rigidness of trying to sell it to public and make it seem like a science project. The musicians always, if we have like an event, I'm going to brought to have these events with all the friends all over the world, right? So we have these performance events where we use this to do something more creative, and that I think allows people to see the possibilities. And again, these Google Map types interfaces, which anyone can use because it's totally free, and visualize the sort of noise pollution in your neighborhood. So there's this also this sort of interesting business model that I was thinking about, and it's kind of really dumb the way we look for homes, especially rental apartments. We go to Julia.com or whatever.com and we look at pictures, we look at metadata, and that's it. What about the sound? What about the smell? What about humidity? What about moisture? All you need to do is leave that in that specific home. So you basically have the agent download the app, leave it there. Now you can browse through the vibe of that space, including moisture, noise levels of that home in real time. So there's also business ways to engage in this. I'm not that interested in those aspects. So there's so many possibilities, and one by one, I think if we introduce these types of applications, artistic research, business models, then I think there might be a possibility that it would spread. And once it does spread, I think it would be really interesting because then you have, again, the Google Earth-like interface, where you have the entire Earth kind of doing this, and being able to visualize that in real time. I think it's going to be amazing. Just artistically see what's going on in Moscow or in Ukraine right now. It's pretty crazy, I have to say, but it's certainly implementable. It's not the technology that keeps us back. It's actually politics. So yeah. Great question.
Yeah, thank you so much for your talk. I'm working a lot in processing this semester, and you caught my attention when you mentioned feature vectors a few times. My question is, what are those specific features that you are yielding from your microphones listening to sound? And like what are the final variables you have to work with inside the process?
So there's a lot of feature vectors that you can extract from sounds, including energy levels, like a spectral centroid, which relates to brightness, spectral flux. So let's say you get 150 of those. So you can use whatever you need to make sense of these features, and you can map them in certain ways to visualize, right, the space in real time, or you can select a couple of them, pass them to a machine learning algorithm, and see if machine learning algorithm can identify what the sound is, and do things like that. So it's really, as we were saying before, it's actually not the technology that's the hindrance. It's actually always our brain that doesn't know what to do with all these nice toys, right? And that's what we provided. We're saying, here's, play with it and see what interesting things you can come up with. It's kind of raw data, right?
What is that data? Is it like waveforms?
Not waveform, because waveforms you can hear the sound and you can see what's going on. So if I did that, I could plot a graph that would look like that would be the energy. Or you can actually the spectral centroid will look like that too, because it's really bright. All the harmonics, all the entire spectrum kind of gets generated and then dissipates quickly. One could be the attack time, like if you do like a crescendo bow, the attack time would be like this. There's a slope. It's another feature.
And those are all like different math equations to do all that.
Basically, all different math equations. Very, very simple things that you would find. Oh, that's obviously what I would do. This sound. If there's a sound that goes like this, it goes to this. You'll say, yeah, this is like a percussive sound. That's more sort of crescendo sound. How do you determine that? By the slope. All these math equations are not there to make your life more miserable. They are sort of an observation of what happens in your life, and just model it and make it as efficient as possible. And there you have it. And that's what all the feature vectors do. Some of the feature vectors are in the time domain, so looking at the waveform and looking at energy. So the other half is in the frequency domain, looking at the spectrum, looking at the frequency components and see how they behave. Just abstracting that. And all that is done for you. So you don't have to do that work, which you can, but you don't have to, which is not that interesting in many ways, but at the same time, learning how to do those things also informs you in terms of what the underlying components are and what sound is. That's how I got into this. Trying to learn what sound is, what makes a violin sound like a violin, what makes a trombone sound like a violin. That's where it starts with feature vectors.
Cool. Thank you so much.
I also really enjoyed the expectancy to have this new way to visualize some of the visible events in the city. But I'm wondering, like, well, there seems like there's already a lot of these devices deployed in cities, as long as there are people with their phones.
Absolutely.
So, like, when I'm using Google Maps to find my way around, like, it's much more helpful to let it track my location, and like, I'm wondering like what sort of benefits might get the user to like allow their audio to be tracked maybe from their pocket, and have a moving, swarming network of these things rather than a fixed.
Exactly.
So,
that is actually part of, so we can download our apps. It's not public yet, and that it allows us to do exactly that. But we're very concerned about privacy issues, and so it's tricky because, as you say, we already have the technology and we're using it, and it's tracking us. Like right now, they know where I am. Actually, no, they don't because it's off. But it is reality that we think that we're not being tracked, but the technology is already there. They know what's really going on. What I'm trying to say is make everything transparent, totally transparent, so that you have control over what's going on and you know exactly what's happening. So yes, our app allows you to do that, so that, let's say, you're kind of driving a car through New York City, you'll be able to see or know, do this, and capture the noise in that way. So absolutely, yes, again, it's as you say, the technology is not that interesting at all, because it's already there. You just tap into that and making it into an app that customizes that functionality. So yes, good question.
Are you sort of saying, we already have Google Maps and we all seem to have accepted that, right?
Yes.
So you're kind of saying, how do we get
You know,
to
what
accept sound tracking just the way we?
sort of incentives could tracking your own sound provide?
I think it's more like it's more of an issue of not tracking your own sounds, but looking at the sound in a collective sense. So one sound is that one ant. That one ant really doesn't do anything. But if you look at the millions of ants together, then you can get information about a space. And that's why every person has to contribute in order to make this successful. And why would a person contribute anything? To learn more about yourself, I think, and the environment. So it's a weird sort of, it's the egg before the chicken, or the chicken before the egg. It's maybe both at the same time. But it's, yeah, we have to do the work in order to make this successful. And that's I think, the way to make it transparent. The nice thing about these types of projects is that artists usually embrace these types of opportunities, and we do crazy things. And hopefully that will make it sort of more well known to the folks who don't do this type of crazy art stuff.
Comment on that I was thinking about during your talk, a couple questions. People volunteer their computers for SETI, or for
That's right.
For distributed computing to do analysis. So
That's right.
So there's a precedent for this kind of thing.
Yes.
You're not ever sending the audio
No.
to the server. So you're sending.
No, you are actually.
You are. So the feature extraction is done.
We're not.
Not done.
So there's two options. So we haven't really decided what to do. So the default option was not to send the audio and just the feature vectors. And those can be for all practical purposes they're not invertible. So they're not invertible. But then I thought it would be really awesome if you could hear the space. So in order to do that, we're doing a voice scrambling. So that everything else you can hear, but when there's voice, you do voice activity detection, and you scramble the voice. So theoretically, you wouldn't be able to hear what is being said, but you'll recognize it as being voice.
And the people sitting at the server.
Right. If you're like Google Maps, and it's like a street view, right? If you look at the street view and you have people like running around, the faces are blurred. That's exactly what we're doing for audio. So it's already there. It's just the audio aspect of that.
And then forgetting about sending the audio, but sending features. So you would have to you're not going to use the processing power of that, of the little.
So we are.
To do the, okay, you
Feature
are going to
extraction.
use that.
Right.
But you mentioned 150 different features you could get from that. Could you send all 150 of those?
Yeah.
Okay.
Those are pretty small in terms of, because you don't even need 16 bits per feature. So
Okay.
we're looking into how we compress that. Yeah.
So what is the sampling rate that you have figured out that you would need for that?
We don't know exactly right now, so we're starting at the highest sampling rate, or the standard sampling rate, 44.1 kilohertz, and it's 16 bits. And then my argument is that no, we don't need that much. Then we'll end up at like maybe 12 or 16 kilohertz, and probably like 8 bits. Because you don't really need to. I made that joke about the cockroach, and that's exactly why I made that joke. You don't really need to hear the cockroach. That's the extra 32 other 16 bits you need to capture the cockroach. Nothing against cockroaches, I don't like them, but it's a separate issue. So that's what I mean. You want to capture the larger items, and for that you don't need a high sample rate. So capture that, and I'm not interested. So we'll see what that sampling rate and the resolution is. We don't know yet, but we're starting at the very top and then degrading signal and then see
You'd be able to hear gunshots, for example.
yeah, unfortunately those, I hate talking about gunshots and whatnot, but that would be the easy one. The sirens, the gunshots, the big sounds, you can just do that like tomorrow if you want to. And, but those are important. Difficult to talk about, but yeah, those are real problems in big cities. And as the cities get bigger, if it's a percentage thing, then you have more gunshots, unfortunately.
So all of this audio information that goes into the server, how long because it can't use the big data issue, but it can't be indefinite. In real time or hundreds of sites, that's just the amount of so
It's not that much data actually. The feature vectors are actually very small, and it's basically like a graph that goes like up and down, and it's every say I think for now it's a couple of milliseconds, but even there we don't need a couple of milliseconds for tracking the history of humanity. I mean, you don't need to go down to milliseconds anyway. Maybe even a second is probably too much, but what's not adequate is doing it every month, which is what people are doing now. The monthly average of this data acquisition is just totally foul, especially for these energy types that are influenced. But yeah, it's not that much data space, and you can probably you have to look into it and compress the old data so that storage-wise it makes sense. And the cloud computing is happening now, and the amount of data storage is not going to be a problem. And I remember in 1987 when I got my first computer, 80 megs of hard disk. Wow. And look what happened now. 80 megs, you can't even, what do you do with the 80 megs? You can't even give that as a present to us. You'd be like, what do you think I am? Type of a situation. So yeah, I think it's 80 megs, 80 terabytes, maybe that's even something. So I think it will become much more, less of a problem as we go into the future. And this is about really a history of Earth. Why would you save any money in that sort of ground? I think it's so important. But it takes convincing, but it's not that expensive compared to other things that you might normally do.
It occurred to me that one benefit that I might get from tracking my audio would be to measure my exposure to sound personally.
Yeah.
And that makes me wonder if there's any way to calibrate the mic on a smartphone so that it could possibly correlate to things like safe exposure levels for my ears.
Absolutely, and it's tricky again because even if we calibrate these things, we have the model number, then it's easily calibratable, if there's such a word. But it also depends on how you hold it, right? If it's in your pocket, who knows? Then calibration doesn't make sense. So I was thinking, how do you do that? I was like, this is called the impulse response, the clap. So it has a speaker, create an impulse response, and if it's a certain space, that's sort of environment. If you do this in a bathroom, lots of reverb, so you can calibrate it that way. And if it's in your pocket, you'll actually be able to calibrate it in the same way. So you kind of know, because if you like do this, you have muffled sound, easily doable, so you actually can get that sort of calibration going. So yeah, we're thinking about these things. It's not going to be a perfect solution, but there are ways to address it. And yeah, as you say, we thought about the idea of what's the best sort of jogging route, and that's an application of it. So there's so many ways to use it. We're just dealing with sound, but imagine looking at other energy types, and it almost becomes like a real-time feng shui thing.
Those open the notion of health.
Yeah.
So right now we have a very flat idea of health for the most part. But then suddenly if you have all these other variables, humidity, sound, whatever, so that becomes an incentive. But we have to, we don't even understand any one of those things, let alone the layers.
Exactly. First steps, very baby steps, but it's interesting in many different ways, especially the artistic sort of side of using this. Can be very interesting. Okay, so thank you for coming.